Hello and welcome back to part 4 of chapter 23. And I'm expecting this to be a shorter video, but we'll just see how things go, because I only have one more derivation that I want to show. But then maybe after that we can work out an example problem, or if I can think of something else that might be good for a discussion point, and we'll see what happens then. But this chapter has been all about Gauss's law, where we can relate charge that has been enclosed by a Gaussian surface to the amount of electric flux that passes through that surface. And so in the first two videos for this chapter, we focused mainly on solving for the electric field that was produced by a certain distribution of charge. And then in the third video, we sort of switched things up, and we started looking for the charge that was present in a given system if we already knew what the field was. And so we're going to actually go back to trying to find the electric field in a given system, just so we can get a little more practice with Gauss's law. And the way that we've been using Gauss's law to solve for an electric field was in the case of having a uniform electric field at all points on the surface of our Gaussian surface. So in other words, whatever container we used to enclose our charge, we chose that container specifically so that it had the same magnitude of field at all points on the surface. The major difference in that idea, all you have to do is go back to part 3 of this chapter, where we had the electric fields that were passing through the different faces of the cube. In that case, we did not have a uniform electric field. So moving on, what we're going to do in this video is we're going to see if we can reproduce the electric field for a disk of charge, a uniform disk of charge. And in addition to that, we also want to see if we can produce the electric field for an infinite sheet of charge. In the previous chapter, we set up the math and the calculus for a disk of charge, and we were able to come to a result. We were able to find the electric field that was being produced a distance of z from the center point of that disk. But then we took the disk and we extended it outward in all directions until we could no longer see the edges of the disk. And at that point, what we had was an infinitely large sheet of charge that extended out in all directions. But we were still able to get an electric field magnitude up at our point that was finite. Even though we had an infinitely large sheet, we still got a finite field expression. And that field expression was sigma over 2 epsilon, if you remember. And sigma was the ratio of charge to area for the sheet. And at first you might be saying, well, this is an infinitely large sheet. It has infinite charge over infinite area. how do we get a definition for sigma? Well, to do that, first of all, you don't try to take a ratio of the entire sheet. Instead, you take a sample of that sheet, like a disk. And on that disk, there will be a finite amount of charge, hence the enclosed charge, versus a finite amount of surface area, which in this case would be the area that the disk is taking up at radius big R. So that's what we want to try with this particular system. And then if we can reproduce what we had for the disk, then maybe we can reproduce what we had for the infinite sheet. All right, so I'm going to draw a large sheet that has uniform charge distribution. That's always going to be our first condition for any of these problems. We want that uniform charge distribution. So we have this infinite sheet of charge. It extends out in all directions, and I want to know what is the electric field that is being produced a distance of z above that infinite sheet. So right away, the benefit of having this infinite sheet is that we can argue that we are right in the middle of the sheet, and therefore all of the electric field lines that are being sent up to that point in space are going to have all of the horizontal components canceling out. It's only going to be the vertical components of those field lines that will survive. So that should sound familiar, especially given how many times we had to modify the math in those calculus derivations. But now this is just a matter of the geometry. We know that at this point we are only going to see electric field lines that point up. But if this is the midpoint of our infinitely large sheet, what about some other point on the sheet? Well, if the sheet is infinitely large, then technically that should be the midpoint as well, and that means that there should be another point, a distance of z above the sheet, that also has the same electric field magnitude as the previous point. And so now what I can do is I can start mapping out, oops, wrong color there. I can start mapping out a literal surface above the sheet where we have all the same electric field magnitude values. In other words, there's basically a sheet above our sheet, and every point on that sheet has a uniform electric field magnitude. Okay, that's a start, because for Gauss's law, I need to have some kind of a surface for a container that I can put around my charge, and I need all the points on that surface to have the same field magnitude. And the reason for that is because it just makes it so much easier if I can bring the electric field expression outside of my integral. And the only way I can do that is if the field is uniform. Well, the infinite sheet of charge that we're using here is effectively going to produce an infinite sheet where our electric field lines are uniform. So basically everywhere a distance of z above our sheet of charge is where we have our uniform electric field values. And so it might make sense to use that as part of our container, except that I can't have an infinite surface area for my container. Again, I can't expect to try and use the entire sheet and the entire charge. I'm going to have to scale it down to some kind of a sample, like a disk. So let's try that. Instead of trying to use the entire area, let's just scale it down to a disk. So even though I'm not using the entire area, if I scaled it down to a disk, well, every point on the surface of that disk is going to see the same electric field magnitude passing through it. So we can use that. That's not a problem. Those electric field lines, however, where are they coming from? We know they're coming from the charges down below on the actual sheet of charge, but I need to figure out a way to enclose some of that charge. Right now I just have a surface area for the electric field lines to pass through. I haven't contained any charge yet. So what I'm going to do is I'm going to draw a little dashed line that comes down here, and I'll draw another dashed line that comes down here. And if I were to just drop that disk down onto the surface of the infinitely charged sheet, then the sampling of charge would be that of a disk. I would effectively be sampling just this much charge. And then if I make those lines solid, and maybe even extend this a little bit below that infinitely charged sheet, well, I now have a container. My container is in the shape of this cylinder, and the cylinder is enclosing charge right along this plane of intersection. So this cylinder drops through basically like a cookie cutter, and it samples that disk of charge that was on the infinite sheet. And so now I have an enclosed charge value. There's a certain amount of charge that has been enclosed by that circle. And now we can focus our attentions on how that enclosed charge relates to the electric field that is passing through the surface area up top. Now you might be asking yourselves, well, this cylinder also has a surface area along the drum portion. So if we go all the way around the cylinder here, you know, there's surface area associated with that drum portion. And aren't there going to be electric field lines that pass through that? And the answer is yes, there will be. But let's take this charge right here and consider what it does to the drum portion of that cylinder with respect to its electric field lines. So here we go. I'm going to draw some field lines from that charge, and goes into the cylinder and then back out. Goes into the cylinder and then back out. Goes into the cylinder and then back out. And so everything about the field lines from the sheet of charge, they will pass through the walls of the cylinder, but the net flux that they provide is going to be zero. The only charge in this system that is actually going to provide a non-zero flux is the charge that was just contained by our Gaussian surface. So this cylinder has become our Gaussian surface. We have contained some charge. How much charge did we contain? Well, that charge that we contained is going to be based on the ratio of charge to unit area. The area that we just carved out there is the area of a circle. And, well, what is that ratio of charge to unit area called? It's called sigma. That means that we can write the enclosed charge as sigma times the cross-sectional area of the sample of charge that we just took from that sheet. So we have sigma times the area that we just sampled. And that information can now be brought down and used in Gauss's law. So we now have an enclosed charge of sigma pi r squared equals epsilon. And we've already argued that the electric field should be uniform at all points as they pass through that end cap of the cylinder. And so we can bring the electric field expression outside of the integral after we take care of the dot product. We still have that dot product in there. So let's take a moment to evaluate our dot product. Our dot product is hiding a cosine relationship. That cosine is relating the angle between the electric field vector and the area vector. We can see the electric field vector is pointing straight up, while the end cap of our cylinder, which way is that pointing? Which way is it facing? And it is also facing up. That means we have a 0-degree relationship between our vectors. And so cosine of 0 just becomes 1. We now have the integral of e dA. E can now be brought out front. And we're left with integrating about the surface of our container. So again, the side walls of our cylinder are not going to provide any net flux. We've already seen that the field lines are just going to pass straight through. They're not going to contribute anything. It's only going to be the end cap that provides any flux, and so we're just going to worry about the area of that end cap, which is the area of a circle, pi r squared. Well, now look what happens. I have the sigma pi r squared on one side, and now I have pi r squared on the other side because of the integral of the surface area. And so my pi r squareds drop out, and I'm left with an electric field that equals sigma over epsilon naught. And at this point you're saying, well, yeah, but up above, you know, if you remember the last time we did this for the infinite sheet, we actually got an electric field that was equal to half of that amount. So why are we getting twice as much field now? Well, there's a slight bit that we kind of skimmed over, and that is that we don't just have an area of pi r squared where our electric field lines are passing through. We have twice that amount. There's twice as much surface area for our electric field lines to pass through, because that disk of charge that we sampled, it's not just going to be sending electric field lines up, it's also going to be sending field lines down. And so we have to consider both ends of the cylinder, and that means considering twice as much surface area. And so we'll have to incorporate a 2 with the integral of the surface area, and then that's going to give us exactly what we were expecting for the magnitude for the electric field of an infinite sheet of charge. Now, one thing that I will bring to your attention, let's look right about here in the steps of our work. I'm going to simplify this a little bit. We have the sigma pi r squared, and that was how we represented the enclosed charge from our charge sampling. So we had this disk right here where we sampled a certain amount of charge off of that disk, and so sigma was the ratio of that charge to the area that we sampled. Well, I'm going to simplify that a little bit further. I'm just going to call that A for area. And so the enclosed charge becomes sigma times the enclosed area. So our equation down here now looks like sigma times A epsilon E. This area came from the fact that we had to integrate about the surface of our container. Well, how did the surface of our container compare to the cross-sectional area of our sample of charge? Well, they're exactly the same areas. I have an area of pi r squared where I sampled the charge, and I have an area of pi r squared when we get up to that area of space where we try to measure the electric field. And so it turns out that in all of the mathematics here, it doesn't matter what shape I try to use for my charge sampling. And so just to show you what I mean, previously here we sampled this infinite sheet using a circular sample of charge. But what if we were to instead take a rectangular sample of charge? Well, if we then translate that up to the point in space where we want to measure the electric field, well, the cross-section of this area up here where we're trying to measure the electric field is the same as the cross-section of our charge sampling. And so we could just as easily make another Gaussian container. This time, instead of it being a cylinder, it would be some kind of rectangular prism. But that means that we would have to take the area of our charge sample and pair that up with sigma, but then we'd have to take the area of our Gaussian surface where the electric field lines are passing through and stick that into the integral portion, and well, those are just going to cancel out again, and the only things that remain in the mathematics are the sigma, epsilon, and electric field expression. And so all of that is just going to condense back to what we got before. Now you might be asking yourself, where's the 2? Well, just extend your rectangular prism down, and there's the second surface area of your Gaussian surface that you need to make the 2 there. Alright, so that effectively brings us to the end of the Chapter 23 material. Now you will notice that I did not actually use Gauss's law to find the electric field that is produced by a disk of charge. And that is because with a disk of charge, we do not have the luxury of all of the symmetry that we had with the infinite sheet of charge. If we look at the electric field that is produced right directly above the center point of a disk, we get an electric field that has only a vertical component. All of the horizontal components canceled out due to the symmetry. But the moment I deviate from that location, I no longer have the luxury of that that symmetry. I'm going to have certain electric charges that are further away than their evil twins, and that's going to result in electric field lines that are not uniform. Whether it's a magnitude issue or a direction issue, we are not going to be able to map out that flat surface above the finite disk the way that we were with the infinite sheet. And so because of this, because I no longer have the symmetry at these other points in space, it's going to make trying to use Gauss's law all the more difficult. Remember, Gauss's law works really, really well for symmetric systems, but the moment we deviate from that symmetry, it's no good anymore. We would be much better suited to going back to the calculus approach. Likewise, for a ring of charge, we did not use Gauss's law for a ring of charge. Basically for the same reason. If we had a ring of charge and we try to measure the electric field that is being generated by that ring right above the center point, well, we have a lot of symmetry that we can take advantage of, but the moment we deviate from that center point, we no longer have that symmetry to enjoy. And so trying to use Gauss's law to map out an area where the electric field is uniform is going to be incredibly difficult. And even if we could do that, we would then have to contend with the idea of trying to integrate about the surface of whatever container we try to use to contain these charge distributions. And that is almost a nightmare to try to think about. And then for something like an electric dipole, could you use Gauss's law for that? Could you put some kind of a container around this system of charge and get all the points on the surface of that container to have a uniform field? And I can't think of any way to do that. Plus, if you were to try to contain this dipole with any kind of container, what would technically be the enclosed charge of your system? Well, you've got one charge of positive Q, you've got another charge of negative Q, and so you've got a net charge of 0. If you tried to enclose that dipole with any kind of shape, doesn't matter what the geometry is, if you contain that entire dipole with some kind of Gaussian surface, then you're going to get an electric field of 0 from the math. Gauss's law is actually not going to work. And so we would again probably be better off just trying to use the individual point expressions and add them together at that location in space. When we went through and we did the derivation for the dipole, we actually derived the electric field directly above the dipole, and the math was not as simple as we might have thought. There was actually about 3 pages of algebra that I skipped over, and we just jumped to the end result. But the reason why our author wanted to use a point that was directly above the dipole was so that we could keep everything in one dimension. And this way we didn't have to break anything up into components. Well, now if we move over here, not only do you have to worry about those 3 pages of algebra, but now you probably have to add a few more pages to contend with the trigonometry that would be required to break up those vector components of your electric fields and add them together. So Gauss's law, don't get me wrong, it's great. It works super well for these symmetric systems, and some systems, even though they might look symmetric, like a disk, that symmetry all depends upon where you're trying to measure from. And as we can see now, not all points out in space are going to have a symmetric treatment in terms of how the electric fields behave. All right, so that is the end of chapter 23. We will revisit some of the Gauss's law methods in future chapters, because from time to time we'll run into some situations where we need to know the electric field, and if we're given the choice of using the calculus approach or the Gauss's law approach, I will always try the Gauss's law approach first, just because if it works, it's going to work very quick, and the math required is just nowhere near as demanding as what some of those calculus methods were. So we're going to close it there, and I'll see you for the chapter 24 material.